every knowledge representation system, like logic, probabilistic logic and so on, have these characteristics. It has a syntax. The syntax has an underlying semantics. And then they all have an inference procedure, which is the main reason why we are studying it. We want to prove theorems, or we want to prove new facts, or we want to see which fact is in line with what you have said, and so on and so forth. So they all have inference procedures. These are algorithms. And then the algorithms will have some complexity, right? The complexity is what is the amount of time it takes to prove a certain thing or to make a certain inference. And these algorithms have two important properties. These properties are soundness and completeness. You would often hear the term sound and complete algorithm. This is a very commonly used term. So let us understand what it means to be a sound algorithm and what it means to be a complete algorithm. We will talk about that in today's lecture. And then in addition to all these, we will have a knowledge base. This knowledge base are the set of facts associated with a particular problem or situation at hand. And this would maintain all these facts in a sentence which would be syntactically correct and will have an associated semantic meaning. Okay? So this is how it is going to work. You will have a knowledge base. This knowledge base will have a domain specific content in it. The knowledge base will have Vishwajit sitting in chair 25 and Divyanshu sitting in chair 77. Then, so therefore, as it says, the slide says, knowledge base is the set of sentences written in a formal language. And where does this language come from? It comes from the syntax of the particular underlying logical representation that we are using, the language that we are using. This would be declarative. Declarative means that I would explicitly tell the system what it needs to know, or what we know about the world so far. We would explicitly tell the system in a logical representation, and all of that would be stored in its knowledge base. Then we can ask the system for specific questions. We can say, based on this, what do you know about a particular fact? And the system will be looking at its knowledge. It will look at its knowledge and make some inferences. And these inferences will be made by an associated inference engine, which will have some kind of a domain independent algorithm running. It would take all these domain specific facts and run its algorithm on top of these facts to generate new inferences based on the questions that have been asked. And so this is called the general reasoning process. So agents can be viewed at the knowledge level, what they know regardless of how they are implemented, and or at the implementation level based on the data structures in the knowledge base and the algorithms that are used to manipulate them. And in the previous world, there used to be expert systems. You may have heard this term. It was the rage once upon a time. People used to say that expert system is going to solve AI. And what would they do? They would have the experts write knowledge in a logical representation and give it to the system to make inferences. One such logical representation would be about symptoms and diseases and treatments and tests. A set of doctors would say that symptom 1 is seen with disease 3. Symptom 5 is seen with disease 4. Disease 3 is treated by treatment 4. Disease 3 is also treated by treatment 7. Disease 3 is diagnosed by test 7, and so on and so forth. Somebody will write this whole knowledge of medicine in this expert system. And then I will give a new situation to the machine. I will say that this person has symptom 3, symptom 7, symptom 8, we have done test 6 that is positive, blah, 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 blah. Tell me what disease does this system have, this patient has, and what medicine do we have to give. This was called expert systems. Everything was being done in some representation of logic. There was a question. The question is, what does domain independent mean? Good question. I did not explain this. Domain independent is a very important term. Suppose I give you this medical diagnosis system. what is my domain and what is my representation? Those are two different things. What is my representation? Some representation of logic. What is my domain? Medicine. My domain is medicine. But eventually, so I am only looking at it in terms of objects and relations and inference algorithms on top of it. Now my domain could have been education. I have, let's say, mathematics. I have to teach them addition, I have to teach them subtraction, but I cannot teach them subtraction before I have taught them addition. I have to teach them multiplication, but before I have taught them addition and subtraction, I cannot teach them multiplication. And I have this graph of the various concepts I have, which concept should be taught earlier, which concept should be taught later. Then I have a new student which has already been taught all these things. I have a goal that I need to teach them these things, and then I ask the system, which topic do I teach them next? Again, all of this can be written down in a logical representation. And then I can do inference to figure out which is the next thing they should be taught, etc., etc. So my domains are the application domains, the particular domains of interest. And my representation is the representation of logic, and my inference algorithm is not about domains. It's general purpose. You give it facts from medicine, it will give you medical diagnosis. You give it facts from education, it will give you educational diagnosis, and so on. Okay. Propositional logic. So now we have to talk about syntax, semantics, and inference algorithms for propositional logic. This is sort of what we are going to do for the rest of these lecture slides. Let us talk about syntax first. Syntax is easy. So what is the atomic syntax? Atomic syntax is just facts. A, B, C, P, Q, X, Y, Z. These are my atomic sentences. And then with each atomic sentence I have literals, two literals, which each atom I have two literals. So with P I have P and not P as my literals. P stands for P is true and not P stands for P is false. Then I have sentences, and P is a sentence, or if S is a sentence, then S1, S2 are sentences, then S1 and S2 are sentences, and if S1, S2 are sentences, then S1 or S2 are sentences, and I can do this recursively. So I can create P and Q, not P, or not Q and R, and so on and so on and so forth. These are all possible syntactically, grammatically accurate sentences that I can create in propositional logic. But if I create sentences like not, and, or, P, that would be called, that would lead to syntactic error, syntax error. You can think of it as C++, right? You have syntax, x equal to y, and if you miss an equal to, it has a different meaning, that is semantics. But if you put in two semicolons, if you forget a semicolon, then that's a syntax error. So basically what syntax is, what is the space of allowed sentences I can speak in this language. And then in the case of logic, I also have syntactic sugar, like P arrow Q also means not P or Q. Okay. Now I have defined the syntax, but as in graphs we have special graphs, trees, in logic we have special syntactic forms. So we have a general form like this, Q and not R implies S, and not of whatever, but then there are specific kinds of forms. One is called the conjunctive normal form or the conjunction normal form, a CNF. Now this is very important because we know that it's a canonical form. A canonical form is one in which any general form can be converted into. I mean any sentence in any form can be converted into this canonical form, a CNF notation. Everybody knows the CNF notation? Okay. So there is a very important rule of logic. Have you heard this joke? Would everybody like a beer? There are three logicians sitting, and the first logician says, I don't know. The second logician says, I don't know. The third logician says, yes. If you got it, you're a logician. If you didn't get it, we'll happily move on. So when you ask a universal quantification question, anybody who doesn't know has to sort of say I don't know, otherwise the answer is, the answer is no, otherwise the answer is yes, right? So, who doesn't know what a CNF form is? Somebody doesn't know, so I need to explain that. So, a CNF form is a form in which it's a conjunction of disjunctions. Now, what is a conjunction? A conjunction is AND operator. What's a disjunction? It's the OR operator. So, when I have conjunction of disjunction, so whenever my statement says that many things are true and the things that are true are inside it, many things are disjunction. This is true or that is true or that is true. That is called a CNF form. I also have a DNF form, a disjunctive normal form, which is a disjunction of conjunctions. When we were in 11th and 12th, we used to study an SOP or a POS. SOP was sum of product and POS was product of sum, and we always liked the sum of product. What is the sum of product in our notation? DNF. DNF, why? Because at the top level I have plus, which is equivalent to disjunction here. So, it's a disjunction of conjunctions. Whereas a POS notation is CNF. Now, we will be using CNF notation heavily. And because of that, we will define a simple set way of representing it. And the set way of representing it is, inside the set I have parentheses. Each parenthesis is one disjunction. And I will represent them by commas, and then between two parentheses I will have a comma, and each parenthesis is a disjunction, and then all the parentheses have a conjunction between them. So, a formula not Q or R or S and not S or not ST, not T becomes a set of parentheses not Q comma R comma S and parentheses not S comma not T. In fact, each of these parentheses or each such disjunction is called a clause. It's just a term. So, we have two clauses in this conjunctive normal form. One is not Q R S, one is not S and not T, not S comma not T. So, I have two clauses. Now, another very important question. What does an empty clause mean and what does an empty formula mean? What does empty mean here? So, empty is like 0. What is the 0 for addition? What number when added does not change the value? 0. What is the 0 of multiplication? 1. What number when multiplied to something leads to the same thing? So, this is the notion of emptiness. 0. This is a set theoretic phenomenon. Have you done group theoretic? Have you done groups, rings and fields? Probably not. But if you study algebra, then you will realize that everything has a 0. Every operator often has a 0, and you have to figure out 0, and the meaning of 0 is x operator 0 should be equal to x. So, let us talk about empty clauses. Now, a clause is a disjunction. What is the 0 of the disjunction operator? True or false? False. On the other hand, what is the 0 of a conjunction operator? True or false? True. So, an empty clause therefore is a disjunction. So, an empty clause is false. On the other hand, a formula which has no clause, an empty formula is true. Okay, this will take you some time to absorb. So, I understand these are new things for you, right? So, if I give you no formula, then my statement is vacuously true. But if I give you a clause, but there is nothing inside the clause, then there is no way I can make this clause true, and therefore this clause is vacuously false, and the whole formula is vacuously false. It will take you some time to absorb this. We will keep going, however, and we will come back to this point when we use it. Okay, we will use it. Okay. Binary clauses are those where there are only one or two literals per clause and horn clauses are very important when you have exactly 0 or 1 positive literal per clause. So that means not Q or not R or S is a horn clause, not S or not T is a horn clause, but A or B is not a horn clause because they are two positive clauses. And why are they important? Because they actually represent a very important kind of a implication relation. So actually not Q or not R or S is equivalent to Q and R implies S. You can do the logic conversion. Q and R implies S, which basically means not of Q and R or S, and not of Q and R when you do the distribution becomes not Q or not R. So these are actually really important to study, and so we will study them. Okay. So this is syntax.